Next we can discuss about how to generate SIC machine code corresponding to a given program. So in the case of SIC we will have a number of addressing modes and a different instruction format. So the program will be more easy as compared to the SIC because we will have a more number of instructions. In the case of SIC architecture, there is only two addressing modes. They are direct addressing mode and indexed addressing mode. There is no immediate addressing mode or relative addressing modes. So but here in SIC we can use immediate addressing mode, relative addressing mode and extended addressing modes. So here to specify immediate addressing mode, we can use hash symbol. So this is a simple program. This program will do the string copy operation. That will copy the string stored at one memory location into another. That is here str1 and str2. There str1 is a string constant stored at a particular memory location, and str2 is a buffer. So what we are doing is we will copy the string from this string constant from this location into str2. Okay, so we can consider our program like this. So how the memory will be allocated? These two are our assembler directives: str2 byte C GC SKPM, str1 byte C GC SKPM, and str2 reserve byte 7. So corresponding to this first assembler directive str1 byte C GC SKPM, then that will allocate, that will create a string constant here, that is str1 str1 and with value GC SKPM G E C S K P M. This will create a string constant like this. Then the second directive str2 reserve byte 7, that will create a byte array with name str2. So our aim is to copy the string constant to this byte array. That is this simple program, and then we will generate the machine code corresponding to this program. Okay, that's our aim. Then first instruction is LDT7. So in the case of SIC we will have a number of general purpose registers also. So one such register is T register. So first instruction is LDT7. That is the immediate. This is an immediate type instruction, and store the value 7 into register T. Okay, so the register T will have a value 7. 7 will be stored here. Then next instruction is LDX0. That means load the value 0 into index register X. That is here the value will become 0. Okay. Then this instruction LDCH str1 X. This instruction will load a single character into accumulator from the memory location str1 plus X. X is the index register. So this is actually an indexed addressing mode. Here we are using indexed addressing mode. Comma X means that indicates indexed addressing mode. So the address of str1 is 200 H. Then the value of X will be added with that. Current value of X is 0. So str1 plus X will be 200 itself. And the value present at that memory location will be loaded into accumulator. That is, this will be loaded into accumulator, single character. So CH means character. So this G will be loaded here. Then next instruction is STCH str2 X. That means store the single character present within the accumulator into a memory location addressed by str2 plus X. This here also we are using indexed addressing mode. So the address of str2 is 207 plus x means x value is 0, so this address itself. So the value G will be stored here. Then next instruction is this one, TIXR T. That means increment the value of X register or index register by 1 and compare that value with the T register. Based on that, set the condition code, whether less than, greater than, equal, etc. within the flag register. That is the working of the TIXR instruction. So here x value will become 0 will be changed into 1. 0 will be changed into 1. Then that value compared with t. Okay, then next instruction is JLT move CH. That is if the condition code is less than, that is jump on less than, to label move CH. Move CH is the label here. Okay. So in this case that will be less than. So what will happen? LDCH str1 comma x will be again executed. Now the value of the str1 comma x is 200 plus 1. That means 201, because the x value is now 1. So this value will be this value E will be copied into here, and that will be stored into here, because STCH str2 comma x. Here this will store the value present within the accumulator into memory location pointed or addressed by str2 plus x. The address of str2 is 207 plus value of x is 1, that is 208. So here E will be stored. Okay. Then again TIXR T. That means this value x register value will be incremented by 1. This will become 2, and that value will be compared with 7 or this T register. Then here also JLT moves it, so jump to this instruction. This will be repeated and all the values will be stored here. GEC S K P M. Finally the value of the this register will become X register will become 7. That is all the 7 letters are copied. This will become 7, and while checking this condition JLT, now the condition will become equal. So JLT move CH will not satisfy, and the execution will stop. That is the working of this one, this program. Then next is we have to consider the machine code generated corresponding to this program, this SIC XC program. നമ്മൾ SIC യുടെ കേസിലുള്ള മെഷീൻ കോഡ് നമ്മൾ മുമ്പ് പറഞ്ഞതാണ്. SIC XC യുടെ കേസിലാണെങ്കിൽ എന്തൊക്കെയായിരിക്കും ഇതിനകത്ത് മാറ്റങ്ങൾ വരുന്നതെന്നുള്ളതാണ്. So we already studied that the format, we have different formats for SIC XC instruction, but the main one common format is format 3 or 4. Format 3 or 4. If E is equal to 1, then format 4. If E is equal to 0, then format 3. Then we will have two other format also, format 1 and format 2. Okay. These are the different mnemonics that we have used in our previous program and the corresponding opcode. What will be the opcode? This is actually in 8-bit format, but we need only 6-bit in the case of SIC XC. In the case of SIC we have to use all the 8 bits, but in SIC XC we need only first 6 bits from the operation code. Okay. Then first we can assume that our program will be, or the code will be loaded at address 250. Okay. first consider the this instruction LDT hash 7. Then what will be the first, we will check the LDT. What is the operation code corresponding to LDT? LDT, the operation code is 74H. All these are hexadecimal values. So 74H. So 74, the binary equivalent will be 0 1 1 1 0 1 0 0. This is the binary equivalent corresponding to 74. But in the case of SIC XE, we need only first 6 bits. Okay, this up to this much. Remaining 2 bits will be anyhow zeros, so that will be ignored. Okay, so that will be written here. 0 0 1 1 then 0 1. So this is the operation code part. Then if you are looking into this one, what type of addressing mode is used here? We are using immediate addressing mode. Hash symbol indicates immediate addressing mode. So we have to use n is equal to 0 and I is equal to 1. That is the configuration or bit pattern corresponding to immediate addressing mode. Then there is no indexed mode. So 0 0 0 0, all these are zeros. Then here we have to mention the immediate value 7. So 0 0 0 0 0 0 0 0 0 1 1 1. So this is the machine code corresponding to LDT 7. Okay, and if we are writing in hexadecimal, that will become, this will be 7 5 0 0 0 7 7 5. That means 7 5 that is 7 5 0 0 0 7. And assume that our program is loading from the address 250 onwards. So 7 5 0 0 0 7. So first instruction is loaded at here from 250H onwards. 3 bytes will be used for that. Okay. And if you are considering the second instruction, that is this one, LDX hash 0. In this case also we are using the immediate addressing mode because hash symbol is there. So we can encode like this. Okay, we can encode like this. So first we have to identify what is the operation code corresponding to LDX. Operation code is 04. Operation code is 04. So 04 means 0 0 0 0 0 1 0 0. This is 04. But we need only first 6 bits. Okay, last 2 bits will be always 0. So 0 0 0 0 0 1. That is we have to fill in the operation code part. Then here also immediate addressing mode. So 0 1, I is equal to 1. Then there is no indexed or relative addressing. So all these we can put as zeros. Then here at the displacement part, here we will direct or immediately we will specify the operand immediately as a part of the instruction itself. So 0. So we have to use 0 in 12 bits. Okay. Then if you are converting into hexadecimal, 0 5 0 0 0 0. Okay. So this will be 0 5 0 0 0. Okay, 0 hexadecimal. This will be the machine code corresponding to instruction LDX hash 0. So we can write that here 0 5 0 0 0 0. Okay, 3 byte will be used for that purpose. Okay. We can consider the next instruction, this one, LDCH str1 comma x. Here there is a comma x, that indicates we have to use the indexed addressing mode. That is clearly mentioned here. And first we can consider the machine code corresponding to LDCH. What is the machine code or operation code corresponding to LDCH? That is 50. Operation code corresponding to LDCH is 50. That we have to use here. 50 means 0 1 0 1 0 0 0 0. This is 50. So we need to consider first 6 bits. That means this 6 bits. Okay. So we can erase this one. Okay. So 0 1 0 1 0 0. So this is our operation code. Then here this will be 1 1, that indicates SIC XC. Then X bit is also 1. Here to mention, that is n is equal to 1, I is equal to 1, that means SIC XC only. And based on this value of n and I, we can have different addressing modes that we already studied. So here we will use n is equal to 1 and I is equal to 1. Then to mention that this is using indexed addressing mode, we will use a 1 at x position. Then this bit will be zeros. Then here we have to specify the address of this one. What is the address of str1? Address of str1 is we already noticed, str1 is 200H. This is the address. Okay, 200H. That we have to mention here. 200H. That is 0010 0000 0000. Okay, and if you are writing in hexadecimal, this will become 5 3 4 2 0 0. Okay, that means 5 3 4 2 0 0 H. Okay, and we can load that value here. 5 3 4 2 0 0. This is our code segment, and the program actual code will be loaded here for execution purpose. Okay, that machine code is now loaded to this location. Then we can consider the next instruction. Okay, next instruction is this one. This one, stch str2 comma x. How the machine code will be generated. So first we need to consider the, here also indexed addressing mode. First we need to consider the operation code corresponding to stch. What is the operation code for stch? Operation code is 54. So 54 means 0 1 0 1 0 1 0 0. Okay, if we are considering the first 6 bits, this will be, so 0 1 0 1, okay, then 0 1. This is the operation code part. Then this will be 1 1 and this indexed, for specifying the indexed addressing mode, x is equal to 1, remaining bits will be zeros. So at the displacement part, we will specify the address of str2 in 12 bit, not in 6. This will be active only in the case of e is equal to 1. Okay, in our case this will be specified by using 12 bit. So we have to specify the address of str2 in 12 bits. str2 address is this one. This is the address corresponding to str2, that is 207. So we have to mention that here 0 0 1 0 0 0 0 0 0 1 1 1. And if you are writing in hexadecimal, 5, this will become 7, this will become 8, this will become 2 0 7, and so this will be 5 7 8 2 0 7 h. And if you are loading to memory, 5 7 8 2 0 7, 5 7 8 2 0 7. That will be the next instruction. Okay. Next we have to consider the 2 more instructions, and after that we will stop today's class. Okay. Okay. So next instruction we need to consider is TIXRT. That means increment the value of X register, index register by 1, and compare that value with the T register. So here there is a difference. Instead of format 3, in this case we have to use format 2 instruction, and the in format 2, format will be 2 byte instruction, and first 8 bits will be used for opcode. 8 bits will be used for opcode. Then next 4 bits will be used for register 1, and the next 4 bit will be used for register 2. And this format is also called format 2 or register type format. We will specify 2 registers here. That is why register type format. Then what is the operation code corresponding to TIXR? That is B8. B8 is our operation code. So we have to use B8 here. B8 means 1011. That is B, and 1000 B8. Then 2 register fields are there, but in this case we have to use only 1 register, that is the T register only. Okay, so what will be the number corresponding to T register? That we have mentioned in the architecture. Okay, in the previous classes we have mentioned that the number corresponding to T register is 5. That is the number corresponding to T register. Number for accumulator register is 0, and for T register that is 5. So we have to specify that here 0 1 not 1, and this part has no significance in this instruction, so we simply put zeros. Otherwise, in some other instruction, add register 2 registers, in that case we have to use both these registers, but in this case we need only one register, so this one, and the second register part we are just simply that has no significance, we are simply putting all zeros. Okay, so here what will be the hexadecimal equivalent? This is B850. So B850 is a 2-byte instruction. Okay, so we can load that here, B850. Then next is we have to consider the next instruction. Okay, so our next instruction is JLT move ch. Okay, so what is the machine code? Here we will use this instruction itself, this format 3 itself. And what is the machine code or operation code for JLT? That is 38. So we can use that here. 38 means 0011 1000. We will use first 6 bits, that means 0011 10. Okay, then what about this NI XBP? Here we will put both N and I 1, and there is no indexed addressing mode, so 0, then there is no base 0 0. Okay, but in this case, in the case of SIC XC, all the jump instruction will use, in normal case that will use PC relative addressing. PC relative addressing will be used by assembler during assembly process, corresponding to all the jump instructions in normal case. So we have to use a PC relative here. So this P part will be 1. This will be 1 and 0. So here we have to use a PC relative concept for addressing. Already we know that this instruction, now this instruction part will be, this will be 3, and this will be B. Okay, 3B, and this part will be 2. Okay, this part we have to now find out. So if you are loading that 3B 2, this we don't know what is here. Now we don't know. So while executing, how the execution will start? Fetch one instruction. PC initially PC will be point here, then the content of that memory location will be fetched into instruction register, and that will be executed. At that time automatically PC will point to next instruction. Then next instruction, the next instruction will be fetched or loaded, and that will be while executing that PC will automatically point to next like that. So after fetching this instruction, PC will automatically point to here. Okay, program counter, PC will point to here. So we have to mention the address with respect to PC. So with respect to this address, so where we have to jump to the move ch. Move ch is the label here. That is the third instruction. That means here. This is the this this is our this instruction. Okay, this corresponds to this instruction. Okay, so we have to jump JLT move ch means we have to jump into here from here. After fetching this instruction, PC is now here. So up to എത്ര ബാക്കിലോട്ട് നമുക്ക് ജമ്പ് ചെയ്യണം? 1 2 3 4 5 6 7 8 9 10 11. So we have to jump 11 bytes ബാക്കിലോട്ടാണ് നമ്മൾ ജമ്പ് ചെയ്യേണ്ടത്. അപ്പോൾ അതുകൊണ്ട് നമുക്ക് എന്ത് ചെയ്യണം? ഇവിടെ ഒരു നെഗറ്റീവ് ഡിസ്പ്ലേസ്മെൻ്റ് ആണ് മെൻഷൻ ചെയ്യേണ്ടത്. അതായത് -11 we have to use here. -11 means 11 എന്നുള്ളത് നമ്മൾ ബൈനറിയിൽ എങ്ങനെ എഴുതും? ഹെക്സാഡെസിമൽ അല്ല, ഞാൻ ഡെസിമലിലാണ് ഈ -11 നമ്മൾ പറഞ്ഞത്. കൗണ്ട് ആയിരുന്നല്ലോ നമ്മൾ എടുത്തിരുന്നത്. 11 ബൈറ്റ് നമ്മൾ ബാക്കിലോട്ട് ജമ്പ് ചെയ്യണം. സോ വാട്ട് ഈസ് ദി 11? 11 മീൻസ് in 12 bits how we can represent 11? 0 0 0 0 0 0 0 0 then 1 0 1 1. This is our 11. Okay, this is positive 11. So to find the negative 11 we have to find the 2's complement of this one. And what is the 2's complement of this one? എങ്ങനെ നമ്മൾ കാണുന്നത്? 2's complement will be 1 1 1 1 1 1 1 1 0 1 0 0 plus 1 plus 1. Then what will become? This will become the last bit will become so 1. 1's complement ആണ് അതിൻ്റെ കൂടെ 1 കൂടി ആഡ് ചെയ്യും. അപ്പോൾ this is our value that we have to use here, displacement, negative displacement. That is why we are taking the 2's complement. So here 1 1 1 1 1 1 1 1 0 1 0 1. Okay, this corresponds to -11. Okay, -11. Then what will be the hexadecimal equivalent? This will become F, this also F, this is 5, F 5. So the code will be 2 F F F 5. Okay, 2F F 5. That will be the code here. So that is also assembled or translated. 3B 2F F 5. So these are the machine codes corresponding to this simple program. Okay, so this part of this memory is called code segment. The region of the memory that is used for storing the machine code or program code is called code segment, and the region of the memory that is used for storing data, this part, this is called data segment. നമുക്കത് ഇനി നമ്മുടെ ഫർദർ ഡിസ്കഷനകത്തൊക്കെ അത് യൂസ് ചെയ്യും. ഡാറ്റ സെഗ്മെൻറ്റ്, കോഡ് സെഗ്മെൻറ്റ് എന്ന് പറഞ്ഞു. കോഡ് സെഗ്മെൻറ്റ്, ഡാറ്റ സെഗ്മെൻറ്റ് എന്ന് പറഞ്ഞാൽ റീജിയൻ ഓഫ് ദി മെമ്മറി ദാറ്റ് ഈസ് യൂസ്ഡ് ഫോർ സ്റ്റോറിങ് ദി വേരിയബിൾസ് ഓർ അലോക്കേറ്റിംഗ് മെമ്മറി ഫോർ ദി വേരിയബിൾസ് within our program. And code segment means the region of the memory that is used for storing machine code corresponding to our program, actual machine code. That machine code will be executed by our processor. Okay, this is about how to assemble or how to generate machine code corresponding to SIC XC processor. അപ്പോൾ ഇതിൻ്റെ കേസിൽ നമ്മൾ ഡിഫറെൻറ്റ് അഡ്രസ്സിംഗ് മോഡ്സ് ഒക്കെ നമ്മൾ ടച്ച് ചെയ്തിട്ടുണ്ട്. അപ്പോൾ അതിൽ ടച്ച് ചെയ്യാത്ത എന്തൊക്കെയാണെന്ന് വെച്ചാൽ ഇൻഡയറക്റ്റ് അഡ്രസ്സിംഗ് മോഡ് നമ്മൾ ഇതിനകത്ത് പറഞ്ഞിട്ടില്ല ഈ ഒരു എക്സാമ്പിളിൻ്റെ കേസിൽ. അതുപോലെ എന്താണ് എക്സ്റ്റൻഡ് അഡ്രസ്സിംഗ് ഫോർമാറ്റ് അതൊന്നും ഇതിനകത്ത് പറഞ്ഞിട്ടില്ല. അതുപോലെ ഇംപ്ലിസിറ്റ് ആയത് ഫസ്റ്റ് 1 ബൈറ്റ് ഇൻസ്ട്രക്ഷൻ ഫോർമാറ്റ്. അപ്പോൾ അതൊക്കെ നിങ്ങൾ നേരത്തെ പഠിച്ചിട്ടുള്ളതാണ്. അപ്പോൾ നിങ്ങൾക്ക് നിങ്ങൾ അസൈൻമെൻറ്റ് കൂടി തരുമ്പോൾ അത് ക്ലിയർ ആവുമെന്ന് ഞാൻ വിചാരിക്കും. ഓക്കെ, ഇത്രയും പാർട്ട് ഏകദേശം ക്ലിയർ ആയി എന്നാണ് ഞാൻ വിചാരിക്കുന്നത്.